Okay, lab 2. Can we model the motion of an object that is dropped from rest that falls straight down? Okay, to model this correctly, we first obtain data from our observations from tracker, and we note the forces from our surroundings that are acting on our system that contribute to Fnet. This is difficult because we typically can't see a force. So we're looking for what agents exert a force on our system. We use our knowledge and experience. We note that our video is recorded at 30 frames per second, so that's the time between each frame that's 1/30th of a second. So our 30 frames per second is our video time scale. Our length scale, and you'll note this from the student, he's 6'3", and that's 1.923 meters. We set up a coordinate system, and the origin is actually at the center of the paper, and that is just before the object is dropped. The axis is aligned. You'll notice that it does have a tilt there. The camera is tilted when the video was made. We tilted it to align with the y-axis with the direction of motion. So in the negative y direction, the object is falling. The center of mass, that is, we'll be able to extract the position data. That's the center of mass we mark with an eye in each frame that you'll notice as we run it. In many frames the object was blurred, so we just marked the center of the blur, the best estimate for the center of mass. That gives us the average position of the object. So from our analysis, we'll notice that position is a function of time. I'll go ahead and run this so you can see. Next, we use our information from our, we take our information that we just observed, and then we add in our initial conditions into Python. So from our video, we now extract that information, we use it in a modeling program. And now we use we add in our initial conditions. This includes the mass of the paper, which is 0.00293 kilograms, our initial position vector, and our initial velocity vector at 0 velocity, and our start time at 0. Next, we look at another initialization area on our Python program. You have to make sure that delta t is small enough here, so when it's compared to the duration of the observation, which would have been 0.5 from our video. We should start at 0 and then it goes to 0.5, so we have to make delta t small. And we have to show interactions. So within this, because it's not a constant velocity, you saw that it didn't have a straight line or slope. You saw that there was a curve. So then obviously there was, for us, we're going to include gravity. So for our model weight, we need to specify the constant g and the magnitude of the weight force, and we need to show a direction for that, the weight, and that will be listed here. So we define the axis unit vector j hat in the direction of the weight force. Next, we look at our calculation loop, and when we look at that, this is sort of where we do the motion prediction. We use Newton's second law, and a lot of this we have used in the past in our last, where we basically use velocity predictions to update the positions, and from that, and we use t is minus negative is less than 0.5, and that's consistent with the time of our video. And the most important thing that we're going to include in this part here is actually going to include the weight force as part of our force net. So we have to specify force net. That's the non-zero net force of the surrounding on our system on our object. We'll assume the net force is due to Earth's gravitational pull, which is the weight. We translate the weight into the computer code. And now we are going to, with our initial conditions set, our other initialization and calculation loop, we're ready to run the module. And we look at that, and it's roughly about the same as our observations. This was the data that we arrived at with tracker data, our experimental position versus time, and you'll notice that it's roughly looks pretty accurate, and we start at T0 at negative 0.002 meters. That's our origin. The object was at rest, and again, it was moving at zero velocity. Let's look at our results here. My results are not looking too good, and this could be a few things. It could be the axis, the direction due to tilt. When I set that, I may not have aligned that. Again, this is we're comparing our experimental, which is the blue dots, to our model predictions, which is the red line, and our axis is labeled position versus time. And so now we're looking at we're comparing our data from our both the experimental and model. Again, it could be the axis tilt. It also could be the model, and it sort of underpredicts the model. Actually, underpredicts, so it may suggest the motion may be influenced by another force, and that could be air resistance. That is something additional, that additional interaction with the surroundings, which is the drag force, air resistance. This model could be improved by adding drag force to the calculation loop in the net force, so we would have gravity and the drag force included. That would further detail. The further details could be described by arrows. It's not correctly modeled because we from when the objects drop from rest, because we need to include additional interactions with the surroundings such as air resistance.